Good afternoon, ladies and gentlemen. Welcome back. This is Mr. Chen with MCR3U, Functions 11, Lesson 4, Sinusoidal Applications. Hopefully you got a chance to watch the Lesson 4A, the Ferris wheel problem, and its full solution there. I actually think that's a very useful lesson to make sure you understand the sinusoidal applications that we're going to be looking at. Today, I'm going to take a look at our handout, Lesson 4. This is our final lesson on this unit, Introduction to Periodic Phenomena. Hopefully I'm going to be able to share the screen properly. And hopefully you see on your screen is the links that Dr. Chen has kind of put on the Lesson 4. Hopefully there's no hum this time. I've been getting, again, major feedback, and I have been changing up my microphone. So just bear with me. And so this is my third take. And hopefully this lesson is not going to be so long. I'm trying to make them under 20 minutes. So this first page is the really good applications of what we're supposed to be looking at, of the sinusoidal applications. Please don't try to click on any of those links. I think they're actually out of date, but a pendulum is a good example. A trampoline going up and down, a swing is also a good example of sinusoidal functions. And what we're going to be doing, or what I'm going to be doing with you right now, is walking us through the questions, especially on page 2. Question 1 is taken from the old Nelson 11 book with the roller coaster question. Let's just zoom in really quickly. Let's read it to you. Look up at the moon on a clear night. Sometimes the moon is full and the night sky is very bright. At other times, sometimes there's a new moon with no visible light and the sky is dark. The moon is said to wax from dark to bright and then wane back to dark. And what we have, someone actually collected the data of the visible moon on each night. Notice again, a couple things that probably had to be done was that the location of where they're looking up at the night sky in the right time is the measure of when they're going to see it. They didn't do it for the full 66 days, but they did go from day 1 to day 66. And so what we're going to be doing is plotting this data for the days on the x-axis, and on the y-axis, the percentage of how much they see the moon. So method 1 of the technique that we're going to be looking is, first of all, looking at what's called a scatter plot. You've heard of the word scatter plot from grade 9, because in grade 9, you looked at what's called lines of best fit. In grade 10, you were supposed to be looking at what's called curves of best fit. So in grade 11 math, we're looking at sinusoidal or signs of best fit. Hopefully I've zoomed in enough, and we're going to take our time to do this. This is my third time doing this. Hopefully I'll be even faster. So on day 1, the percentage of the moon is 0.25. So on this value, we have 0.25, and I'm probably right about there. Day 2, 0.18, right down there. Day 3, and let's just correct that actually right now. That is actually not correct. So I'm already making mistakes. Day 3, 0.11, so maybe down there. Day 4 is really low. Day 5 is 0.2, so even smaller. Day 6, notice they're seeing no moon. So no moon. Then day 10, all of a sudden, where's day 10? Day 10 is way over here, and day 10 is 0.11. And then day 15 is 12, 14 to 15. Here, it's 0.57, way up here. Day 20, which is on the x-axis, is 0.99. Very bright moon. Day 21. What does that mean? Well, day 21 is up. Full moon. When the werewolves come out. Day 25 is over here, and it's 0.8. And then, where am I? Day 30, it's 0.32. Day 35 is 0.02, so not even quite Okay, so we're not seeing any moon again. Day 40, 0.14. Day 45, 0.64. Day 50 is 1. Again, another full moon. Day 55, 0.77. Day 60, 0.31. Day 65, 0.01. And day 66, 0. So that's a scatter plot that we have. Let me zoom in case some of you need to see it a bit better. That took me a while. I'm getting better. And so it says, draw the curve of best fit. So we don't connect the dots. We're trying to draw a line that goes through almost all the data points. And let's see if I can do it. It's good enough for now. Let's answer some of these questions of exploration. Starting with day 1. Where's day 1? Day 1 could maybe be right about here. That's 2, that's 1. So 1 is probably right about there. How many days does it take for the shortest complete pattern of the graph to represent or to repeat? This question is basically asking for the cycle. So where do I see that pattern again? Well, I seem to see it on day 1. It seems to be there. And then when do I see it again? Probably right about there. And to me, that's actually day 31. How many days does it take for the shortest complete pattern? So to me, this is 30 days. Starting with day 6, let's use a different color. Let's use this green. Where's day 6? Day 6 is right here. So where do I see that? So day 6 is there, and where do I see that pattern? That day 6, and it seems to be coming up from the bottom, so maybe day 6. Oops, that's not correct. Day 6 was, hopefully you caught my area, ladies and gentlemen. It was down there. Haha. So the other pattern is this one. And I think everyone agrees that's 30 days, because actually day 6, this represents the minimum, or the no moon. On what other day could the graph begin and still repeat? And a lot of you understand this now. Any day. You could have started on any day and see the pattern repeating. You could have chosen the maximums or the full moons. You could have chosen another point when you saw 3/4 of the moon. So part 3, based on the graph, estimate the period of the repeated pattern. And notice all your answers should be question 2. The period is 30 days. Estimate the amplitude of the curve. So since we know the maximum occurs at 1, the minimum occurs at 0, no moon. Amplitude, mathematically, is 0.5. Or some are actually doing it this way from what we looked at already from the Ferris wheel problem. That's the amplitude. So some of you actually also might have done it that way, by actually drawing the equation of the axis or the vertical displacement line. All right? So the EOA is y equals 0.5. So now notice what we're trying to do for question C, 3C. If you use a sine function in the form of y equals sine bx, we should make that minus c plus d, describe the curve. What are the values of a, b, c, and d? Assume the horizontal scale is in radian measure. A lot of you know what I'm going to be doing. just like the Ferris wheel problem that we did, most of us will actually do APDNS, where D stands for the equation of the axis, and that might assist you. So we already know what the amplitude is. That's 0.5. We already know the equation of the axis because we just drew it in, actually. That's also 0.5. We kind of know the period. I used green, but we'll use pink this time. It's 30 days. And the phase shift, because we're using sine, let's see where that sine graph looks. And I'm going to draw a sketch, first of all, of y equals sine x here. Just a refresher. It looks something like that, right? There's our 5 critical points. And you're kind of looking for that pattern. And I think everyone actually sees it right about there. And that's day, I think, 14 for me. So don't feel bad if you got a different day than me. Sometimes you might have 15, some may have 13 or 11. And some you might actually have a period that's not 30 days. Maybe you actually have 28 days or 29 days or 31 or 32. But clearly the period is not 20 days. Clearly the period is not 35. So I think everyone agrees it's plus 14 or 14 days, right? Just to show you our thinking process. So we have to figure out the equation. And you know what? I think you know what we're going to do. Oopsie. I think you know the A value is 0.5. Sine, I'll leave the B value alone a little bit. X minus 14. Why minus? Because it's towards the right. Plus 0.5. So the only thing we have to do is actually deal with that B value. And the B value, since it's saying it's actually in radian measures, we're going to do 2 pi divided by the period, or in this case, 2 pi divided by 30, which equals pi over 15. So notice our B value is this, and that's the equation that we're going to be using. So hopefully that helped. Method 2, when you're seeing that Dr. Chan's handout, this is actually using a graphing program. Oh, and just to go back a little step, the reason why this question is really neat is because it's looking at the moon, and some of you are already connecting that the moon is related to the word month. That's where the word actually comes from, because the months or the moon is a sinusoidal or periodic phenomena, right? And it definitely rotates around our planet Earth in a regular pattern. So method 2 talks about using a graphing calculator, uses technology, using a program called Graphmatica, which we don't use anymore. That's why we can't have a graphing calculator. That's why we can't ask you to do this using your cell phones or anything when you're doing an exam. And what you're supposed to be doing is really just checking the equation right here. Now, it might look a little different because what they did is they actually expanded this form, whereas we've been teaching you this way, factored form. So just be aware that that's their B value, and then if you actually expand it properly, then you should be all right. The only thing I'm going to ask you to probably kind of just check on your own and explore yourself is this question C. See if you could actually answer it. And as well, maybe doing this question D. That's all you really have to do. Let's move on to question 2, though. Hopefully you can read it with me. What I would do for this question is, first of all, sketch out what's happening. And again, you don't need graph paper. Some of you might be better than me that I'm doing this again. Here we go. So that's negative 90 degrees. That's negative 45 degrees. 2, 4, 6, 8, 10. Then we got 45 degrees and 90 degrees. And notice this should actually be 135 degrees. And then finally 180. So please make sure you change that. So let's plot these points. We'll use blue. Negative 90 is 8, so right about here. The negative 6 is negative 45, so down there. The 4 is 0, right about there. 45 is back up to there, to the 6. 90 is back to the 8. 135 is 6, and then 180 back down to 4. So some of you are noticing this kind of weird pattern. And it looks like that. I probably just sketched that poorly. So, do you think you can actually do the AP DNS for this? And I'm going to do this quickly. I think everyone's agreeing with me that the amplitude is 2 units. The equation of the axis is at 6 or plus 6. The period is 180 degrees, because if I go from this maximum to that maximum, that's 180 degrees. Phase shift. Notice I'm going to do this question a little different because I'm trying to introduce something here. I'm going to make that 0, and I'll explain why. I'm going to take this point for our graph. So I'm going to be using cosine to solve this, and we'll explain it in a moment. If you have any questions, though, feel free to contact your peers or email me and ask me questions to clarify, but I'm going to just do this one really quickly with 0. Hopefully you'll understand what I'm talking about when I give you the answer. The answer is going to be y equals 2, because the amplitude is 2. I'm going to use cosine. I'm going to skip maybe we'll do the b value right now. So the b value is 360 degrees divided by 180, which I think everyone agrees that's 2. So that's not a big deal. We're using x, I think. Yep, x. Oops, there was none. So let's just erase that. And it's plus 6. The only catch I'm going to talk about is that a lot of you realize if I sketch out the cosine graph, the base function, it starts at a maximum, goes to a minimum, and then goes back to a maximum. This graph seems to start at a minimum. So how can I relate that? Well, I think some of you know what I'm going to do. I'm going to put a negative, because some of you actually understand what I'm going to say when I write this out. What does it mean when A is negative? And I think you already know the answer. It's a reflection across x-axis. Don't believe me? Don't feel bad. It's okay. You can check by actually taking this maximum at 90 degrees. And notice I'll write that still in our analysis. If I use the right 60 degrees for this chart, which is plus 60, you can actually get the same answer using the same information, except you can always check my work by looking at Desmos or GeoGebra and entering in these two equations. And they're the same. And it kind of makes sense, is because they are congruent. We get the same graph. Finally, I don't think I need to do any more problems with you. I'm just going to highlight some other questions that you might want to do yourself. It's question 3, question 4. From the exercises, question 1, question 4, 5, 7, and I think 8. Those are the only ones I think you might want to actually do. Notice there's been some students that have been asking me, where in the textbook can we find it out? As always, at the end of these packages, where it says AW11, that's our Edison Wesleyan textbook, there's some pages to refer to. And there is actually some answers. If you just scroll through, I'm sure you can figure it out by working backwards sometimes. But as always, if you need some help, please feel free to look at the CEMC resources at your disposal. You can also definitely use Khan Academy to go through a bit further. Big disclaimer, this is American, and it's a good resource. Some of you might have other friends that actually have the Functions 11 textbook from Nelson, and it's an online resource that you can definitely try to choose as well. I want to thank you. Again, hopefully these videos were helpful. I know I might have been mumbling a little bit. It's like the 4th or 5th take I've been doing. So I just want to apologize. And finally, with any of the hums or the YouTube videos, hopefully, I know they don't replace what's going on in the classroom. And just try your best, ladies and gentlemen. There is going to be an assignment that's going to be posted, I think, tomorrow. That's Saturday, April the 18th. And I want to wish you good luck. Just try your best. We will be starting the exponential function soon. Have a nice day.